Welcome back to the deep dive. Today, our mission is to give you what is really the ultimate shortcut to building resilient software.
Yeah, we're going to go beneath the surface. We're looking at why even perfectly written code can lead to systems that are, well, incredibly fragile.
And how this idea of exceptions is maybe your best tool for managing all of that fragility.
Well, when we talk about coding, you're really dealing with three core kinds of failure.
Yeah.
And, I mean, they require completely different mindsets.
Okay.
So first, you have the easy stuff,
Yeah.
the syntax error. You misspelled a function name or you missed a colon.
Right, the interpreter catches it right away. Your code doesn't even run.
Exactly, you fix it. Low-stakes stuff. Then you get into the real headaches.
Logical error.
The silent killer. The code executes perfectly, sequentially, no crashes, nothing. But it calculates the average incorrectly.
Or it deletes the wrong user record. It works, but the outcome is just garbage or dangerous.
Precisely. And that takes rigorous testing to fix, but it's still predictable failure. It lives inside your code's own logic.
But the fragility we see in modern systems, the network dropping, a file suddenly being corrupted, that's the third category, isn't it? The runtime error.
That's it. Your software might be predictable, but the runtime context is anything but.
What do you mean by runtime context?
The file you need might be locked. The user might type hello when you expected a number. A remote server could just time out.
So these are all external, unpredictable events.
Right. And they cause the program to suddenly hit a situation where it just can't proceed normally.
Okay, so let's unpack that. This is where we get into how programming languages formalize that unpredictability.
As exceptions.
Right. The mission for this deep dive is to really master the philosophy and the mechanics behind anticipating and recovering from these runtime errors.
Fundamentally, an exception is a runtime error that gets raised when a normal response is impossible. It's not just a message.
It's an object.
It's a dedicated object, a data structure that gets created. And its entire job is to immediately interrupt the sequential execution of your code.
And they all have a common ancestor.
They do. If you trace the family tree of every single error, they all ultimately derive from base exception.
So let's get into the mechanics of that. This interruption object gets created. What happens when it's raised?
The moment that exception is raised, the program halts. Right there, at that specific line.
And I assume that means any code after that line.
It doesn't get executed. The whole thing just stops. The stack unrolls, and unless something is there to catch it, the program terminates.
But you mentioned that halt can be a tool, that programmers can explicitly raise exceptions. When would you want to actively cause that kind of interruption?
Oh, all the time. Think about input validation or enforcing your own rules. Imagine you're building a custom list class, let's call it even only.
Okay, so only accepts even numbers.
Right. So if a user tries to add the number 5 to this list, a default system error doesn't really make sense. You need to use the raise statement yourself.
To signal that specific rule violation.
Exactly. You'd raise your own, say, odd number not allowed error. You use the same mechanism the language does to enforce your own logic.
Okay, so raising is causing the problem. Handling it is about controlling that interruption. How do we build the safety net?
That's your core defensive tool. The try and accept blocks. You place the dangerous code, the part that might fail, inside the try block.
And that tells the interpreter what?
It tells it, hey, if something goes wrong in here, don't crash the whole program. Instead, execution jumps immediately to the accept block.
Which is where you put your recovery logic.
Right, you can retry the operation, log the failure, maybe substitute a default value. It's how you regain control over the chaos.
But what if that try block involves resources? Like you open a file or connect to a database. If the code fails before you close them, that's a huge problem, isn't it?
It's a massive problem. And this is why the optional, but I would say absolutely critical, finally clause exists.
The cleanup guarantee.
It is. So many developers skip this, but it leads directly to resource leaks. The code inside, finally, is guaranteed to execute.
No matter what happens.
No matter what. Whether an exception happened, whether it was caught, whether the try block finished successfully, it guarantees cleanup happens. Omitting it is like a ticking time bomb.
Okay, give me a real-world consequence. What happens when I skip that finally cleanup?
Imagine you're opening files or database connections. They use system resources, things called file descriptors or sockets. If an error occurs, say a network timeout, and you don't use finally to close that connection,
It just stays open.
it says reserved by the operating system. And if this happens over and over with lots of users, you quickly exhaust your system's available resources.
Which leads to,
severe performance degradation,
yeah.
or even crashing the entire server with an OS because it literally cannot open any new resources for anyone.
Wow. Okay. This is where it gets really interesting then. Beyond just the basics. Since these exceptions are objects in a hierarchy, we have to be smart about how specific we are.
Right. And the simplest but most dangerous choice is to just catch everything.
The naked exception.
That's the one. By catching that generic handler, you are telling your program to catch every single subclass of base exception.
Now hold on. If everything derives from base exception, why is that a bad thing? Why are there two levels, base exception and then exception?
That's a fantastic question. It's subtle. Everything does derive from base exception, but most of the runtime errors you actually want to handle, value error, IO error, type error, they all derive from the next level down, exception.
So what's left in base exception?
The things you almost never want to catch. Critical system interruptions. Keyboard interrupts, which is when the user hits Control-C, system exit. Things that mean the program should stop.
Ah, so if I catch a naked except, or base exception, I'm actually silencing the user's request to kill the program.
Exactly. You're masking catastrophic failures. You're preventing a clean shutdown. It leads right to the best practice rule. Always catch a specific exception type.
Or at the very least, catch the base exception class.
Yes. But never the grandparent, base exception, unless you have a very, very good reason and know you can handle system interrupts.
The source material notes that this is so serious that tools like MyFly will flag it as an error. What does seeing that in a code review signal to you?
It signals a lack of precision, or worse, maybe ignorance about just how severe the failure is that you're hiding.
Whereas if you catch a file not founder,
Then you are telling the next person who reads your code exactly what state you expect the system to be in and exactly what recovery action you planned. The hierarchy enables that precision.
which brings us to another point. Sometimes the built-in exceptions, even specific ones like value error, they aren't expressive enough for our own application's logic.
I'd say they rarely are for complex business logic. I mean, if you're building a banking app, raising a generic value error when someone tries to overdraw an account isn't very helpful.
It doesn't communicate the actual business problem.
Not at all. The system needs to communicate a very specific condition.
So we have to define our own tools. I'd need to create an insufficient funds error.
Absolutely.
Yeah.
This is so critical for making your code maintainable and clear. And the rule is simple. You create a custom exception by making a new class that inherits directly from the standard exception class.
And that puts it in the right place in the hierarchy?
It does. It means it behaves correctly. It won't catch those dangerous system interrupts, but it's still catchable if another developer is looking for general runtime issues while providing that specific context for your error. It turns a simple failure into an addressable business condition.
This brings us to a major philosophical fault line in how developers think about writing robust code.
It really is foundational. It can define the entire feel of a code base.
And the question is, should you spend time checking for problems first, or do you just run the code and see what happens?
Exactly. This defines two very different schools of thought. The first one, and generally the less favored one in the Python world, is LBYL.
Look, before you leap. Sounds very cautious. What does that actually look like in code?
It means you have if statements everywhere, checking every little thing before you try to do it. You check if a file exists, then you open it. You check if a dictionary key exists, then you try to access it.
It's an obsessive kind of caution. What's the drawback to that besides burning a few CPU cycles?
Well, there's duplication of effort, but the big one is race conditions.
Ah, right.
If you check that a file exists, and then right after that you try to open it, there's a tiny window where another process could have deleted that file.
So your check is instantly outdated.
Right. You haven't actually prevented the failure. You just made your code longer, a bit less efficient, and you still have to handle the exception anyway if the file vanishes.
Okay, so in contrast to LBYL, the Python community really leans into the other model.
Yes, the preferred model is EAFP. It's easier to ask for forgiveness than permission.
So you just go for it.
You assume success. You just try to open the file. If the system raises a file not founder, then you catch it and handle that specific failure. The successful path, the happy path, is clean and direct. It isn't cluttered with all these redundant checks.
But this philosophical divide can't be absolute, can it? When does EAFP stop being a good idea? We don't want to use exceptions for just, like, basic control flow.
No, absolutely not. You should not use exceptions to handle things that happen routinely. The source materials are clear on this. Exceptions are for exceptional circumstances.
Even if they're only a little bit exceptional.
Right. But I can see you're thinking of a case where LBYL is necessary.
Yeah, what if the cost of failure is just too high? For instance, dealing with a very slow remote API.
You've hit the exact strategic trade-off. While EAFP is generally preferred, LBYL has mandatory use cases. If the operation inside your try block is extremely costly, like a 10-second network call, you absolutely want to use LBYL to check simple things first.
Like making sure the URL is formatted correctly before you make the call.
Of course. Or for security validation, right? You have to make sure the user has permissions before you try to access a protected resource. You can't just wait for an exception there.
So security checks and validating user input are cheap if statements that prevent expensive or dangerous operations.
Exactly. But when you're dealing with those unpredictable external systems, file access, database calls, network I/O EAFP is brilliant because it handles those inherent race conditions so much more gracefully.
And what's interesting is that even when the final effect of the two approaches is identical, the EAFP code is often just cleaner.
It is, because it separates the successful flow from the error flow. The maintenance programmer can instantly see the intended outcome without having to wade through a dozen prerequisites F-checks.
That brings us to the end of our deep dive. We've really covered a lot of ground here, moving from basic error types all the way to fundamental software philosophy.
Okay, so let's try to review the key strategic takeaways for you, the listener. First, I'd say, is just to embrace the unpredictability of the runtime context and know that exceptions are these powerful objects derived from exception.
Right. And second, master the mechanics. The try, the accept, and please use the finally clause.
Yes, that finally is your non-negotiable insurance policy for cleaning up resources. It prevents those insidious leaks and crashes.
And finally, the big philosophical piece. Adopt EAFP. Execute first, deal with the fallout second, but always be specific.
Yes, no more naked except blocks that mask serious things like keyboard interrupts or system exits.
And that specificity also means customization. You have to be ready to define your own exceptions, like are insufficient funds error when the built-in ones just don't describe your business problem.
For sure.
Now, to really make this knowledge stick, the sources suggest a fantastic way to practice, tying this directly to application design.
Yeah, this is a great recommendation. It says to use object-oriented design and force yourself to define and use at least one custom exception class to solve a real problem.
It helps you move from just being a consumer of exceptions to a designer of robust system rules.
Exactly. And the source material points to two excellent challenges on the Caddis platform for this. The first one is called A New Alphabet, and the second one is Babelfish.
And solving those while really thinking about custom exceptions and the EAFP philosophy would be a perfect way to make all this concrete.
It really would.
So we encourage you to go seek out those challenges, because the true measure of a great developer isn't just writing code that works in the best case. It's about writing code that fails gracefully, recovers smartly, and truly builds resilient systems that expect the unexpected.
It's about asking for forgiveness, not constantly checking for permission.
We'll see you next time on The Deep Dive.